this video, we introduce one of the most powerful types of functions around, an exponential function. You probably heard of it before, exponential growth and decay, but today we're going to see the difference between linear growth and exponential growth. Let's get started. So I want to remind you of something you already know, hopefully. You should remember that if we're talking about a line, we're talking about a situation where our growth or decay is constant, right? The rate of change is constantly increasing by the same fixed number each time. In other words, we have a constant slope, right? So we could write the equation of a line, remember, as y equals mx plus b, right? And we could have, like in the picture here, an equation like y equals 2x. So if you remember the equation y equals 2x, that's really telling you that every time you increase by the x value by 1, you are increasing your y value by 2, right? So if I go right 1, okay, so if I go right 1, I should be going up 2, right 1, up 2, right 1, up 2, etc., or up 2, right 1. So that's why you get a nice constant rate of change. Now, for some things, that model makes a lot of sense, right? Maybe every single day you're increasing the number of carbs that you eat or the number of cars that you sell by the same amount each day. And if that's the case, this is a linear growth. But then there are other things in life which, instead of constantly adding or subtracting the same number from input to input, instead we're maybe doubling each day or tripling each day. So instead of a constant slope, we have a difference where the outputs, if you were to take their ratios, that ratio is constant because you're constantly either doubling or halving or something to that effect. So I notice the difference in my equation. Instead of y equals 2x, for example, now I might have an equation like y equals 2 to the x. You can see here that one of these is linear and one of these is exponential. Now I can tell exponential because x, or the variable, is in the exponent, right? It's the power of the function. Why would that make sense for this situation if I'm doubling? So on day 1, I might be here, then I double up on day 2, and I double up again on day 3, and on day 4, and on day 5, and I keep doubling my value each time. I keep multiplying by 2 over and over again. Now, some situations follow this pattern. Y equals some b. I'll use b for base instead of a. I like b better. Y equals some b to some power x. That's an exponential model where the base is telling you what you're doing over and over again with multiplication. Are you multiplying by a number like 2 or by half, right? Imagine if instead of doubling each time, you were cutting in half each time. Well, then instead of exponential growth, it would look more like exponential decay, and we'll see that in our graphs coming up. But I want you to start noticing the difference in the equations and also the graph, right? Linear growth versus exponential growth, which is very, very rapid. And in the equations, with linear growth, we're looking for mx plus b. And for exponential, we're looking for a variable in the exponent. Take a look again at the tables to your right. Y equals 3 to the x would be exponential growth. You can see what's happening on days 1 through 6. Maybe this is a situation where you have some bacteria growing on a petri dish, or maybe like me, you look up one day at your ceiling and you see spots of mold, right? Day 1, 3 spots. Day 2, 9 spots. Day 3, 27 spots. Day 4, 81 spots of mold. Day 5, 243 spots. Day 6, 729. You got to call the mold guys at this point. This is exponential growth. You are tripling every single day. Very quick growth, okay? It's also very quick decay if you were talking about 1/3 to the x instead, dividing by 3 each time. But on the other hand, what if I have y equals 3x plus 1, right? This is a situation where you're on day 1 starting maybe with $1, and the next day you give someone $3 more, so now they have $4. And the next day you give them $3 more, now they have $7. If you're giving an allowance to your kids, this is getting kind of bad, but it's not as bad as exponential would be. So every day you're increasing by the same number, by 3. You're adding 3 each time. So notice here, you weren't adding the same number each time for exponential. Instead, you were multiplying by the same number each time. So you can already start to see the difference in the two types of growth or decay. Okay, so let's head over to our next slide where we generalize some of these properties for exponential growth and decay. So here we have an example where we're told, okay, suppose you have an x set of values, 1 through 5, and you have outputs, your y set of values, 1.7, 3.4, 6.8, 13.6, 27.2. If I were to ask you, which type of growth do you think this is? It is growing, right, from day 1 to 5? Okay, we agree on that? How is it growing? Am I adding a constant number each time? Am I multiplying by a constant number each time? What's going on? So do I have a constant slope that I'm adding each time? Sorry, slope. Or am I multiplying by a fixed number? What's happening? That's right, I'm actually multiplying by 2 each time, aren't I? I'm doubling each time. If you multiply 1.7 by 2, you get 3.4. 3.4 by 2, you get 6.8. So I'm doubling each time. Maybe this is day 1, day 2, day 3, day 4, etc. You're doubling each time. You're not just adding a fixed number. So it's not linear, but rather this would be exponential. So this would be a situation where you have something like this happening, and it's growing rapidly. Okay, so now let's make our generalizations. What are graphs going to look like if we're talking about exponential growth? Well, exponential growth, like the one on the first screen, we could use y equals 2 to the x as our example here. So y equals 2 to the x would be an example of exponential growth. Now, the reason I say it's exponential growth in this case is because our base, b, is bigger than 0. We're talking about the equation y equals b to the x. So if it's bigger than 1, like 2, we're doubling every day. If it was 3, we'd triple every day. You hopefully get the idea there. But on the other hand, if I was talking about falling or decay, I might have a base like 1/2. Got some nice symmetry going on here, some y-axis symmetry, right? This would be an example of exponential decay when I have y equals parentheses 1/2, or 0.5, the decimal, to the x power. Okay. So exponential decay, exponential growth, they're mirror images of each other because one is doubling and one is halving in this case. They don't have to be 2 and 1/2. I'm just giving you 2 examples. So in the sense where you have decay, your base, b, is between 0 and 1, so make sure that's in your notes somewhere. And in the case of growth, your base here, I think it was supposed to be telling you both of them here, your base b is bigger than 1. So they're both positive, but in one case, your base is bigger than 1, and in the other case, your base is between 0 and 1. Now, what do we expect to happen for 3 easy points? We expect the growth and the decay to look like this, but how can I memorize 3 easy points so that I'm in good shape to start moving these graphs around as needed for real-life situations? Well, the first thing I notice is if it's just b to the x, so base to a power, base to a changing power, all I need to remember is I could input -1, 0, and 1 for x values, and they would spit out some very nice outputs. For example, in the case of y equals 2 to the x, let's take a look at our 3 key points that I would have in this situation. If I input -1, 0, and 1. If I input -1, this is probably the hardest one for some of my students. That would mean 2 to the -1 power. Now, this is not an inverse like we had in our previous video, f inverse. When I have a number to the -1, that really is the reciprocal. That is 1/2. So when I say 2 to the -1, that is 1/2. So that is the reciprocal here. Okay. Then I take 0 and I make that my power. Well, what's 2 to the 0 power going to be? Well, isn't the 0 power always going to give you an answer of 1? You have no copies of 2 that you're multiplying by, so it's like multiplying by 1. Okay. What if I input 1 as my exponent? What is 2 to the 1 going to be? Yeah, that's 1 copy of 2 that you're multiplying by, or just 2. So now I can see which 3 points on my graph I could immediately plot. 0, 1 would be that point there. So that's my point 0, comma, 1. -1, 1/2 would be around here, -1, comma, half. And 1, comma, 2, 1, 2 would be around here. So those would be 3 very easy points that I could then draw my exponential curve, or I guess in your case like this, draw my exponential curve, and I would have a growth model, okay? The beauty of a model is you can make predictions. Now if I want to know what to expect, if this is my mold example, what to expect on day 10, I simply input 10 into my function, right? And get 2 to the 10th power, and I would see where that point would be. It's shooting up very quickly. You can see that's not such good news if you're talking about mold, but if you were talking about income or interest earned, this would be awesome. Okay. On the other hand, the same applies to exponential decay. Suppose we consider y equals 1/2 to the x power. So in this situation, same thing happens. You plug in -1 for your input, 0 for your input, and 1 for your input. And check out what your outputs would be, your y values. If you input -1, you're going to have 1/2 to the -1, which really means take the reciprocal of 1/2. What is the reciprocal of 1/2? 2/1, or just 2. So that's the point, -1, comma, 2. That's up here. On the other hand, if you input 0, so that was 2. If you input 0, you would have 1/2 to the 0 power. Anything to the 0 power is 1. So 0, 1 is there. So that's the same point. Don't need to rewrite it. And finally, if you input 1, what happens? That's right. You would have 1/2 to the first power, which is just 1/2. So check out where that is. 1, half, right there. 1, half. Okay, so we can see here that if I have 3 key points memorized, and so I will ask you to memorize these 3 points for any function y equals base to a variable x. We expect you to know those 3 because eventually you're going to be expected to move these graphs depending on the model that you're trying to talk about. The other thing I would like for you to memorize is what is happening as you go toward the extremes, right? As your x values get bigger and smaller forever, is there an output, is there a y value that we are tending to get closer and closer to but not ever touching? For example, as I continue going along this way to the right forever, it looks like I'm getting closer and closer to y equals 0, and similarly for the red curve, as I go to the left forever, its graph is approaching 0. So it looks like I'm getting closer and closer to this line. Now I'll never touch that because if you understand what's happening, in this case you're dividing by 2 at the extremes over and over again. And if you keep dividing bigger and bigger numbers or more and more negative numbers by 2, you'll get closer and closer to 0, but you won't ever reach 0. It's the idea of continuing to cut in half over and over again for eternity. So that would mean that you would have a horizontal asymptote. We've studied those in talking about rational functions, but now they come up again. It's an idea as you go toward the extremes if you're approaching a y value. And in this case we're approaching y equals 0 at the extremes. What about the domain? Can we memorize that as well for exponential functions y equals b to the x? Yeah, we should be able to. Domain is a set of all x values which are allowed. So what would the domain be for these 2 graphs? They're both the same actually. Yeah, you could actually go to the left forever and the right forever, which means your domain is negative infinity toward infinity. In other words, there are no input restrictions for x. They could be negative, they could be positive, they could be 0. But for range, are there some outputs which we never reach? Are there some y values which we don't get to? Yeah, we don't get to negative y values unless we move these graphs. So originally, we're always above 0. So parentheses 0 toward infinity. That means any y value bigger than 0 has a chance of being reached. So this was talking about your money earned in a bank. That's kind of good news because you're never going to go below 0. So that's kind of cool if that was the model. Okay, so let's head over to our next example where we try to graph exponential functions by remembering these 3 key points. So make sure they're written down somewhere. We have this equation, f of x equals 3 to the x minus 2. It asks you to graph the function with 3 points. Tell me about the asymptote, the domain, and the range. So let's really take our time and make sure we understand what's going on. Y equals 3 to the x. So my original would be y equals 3 to the x, and this is exponential growth or decay. It would be growth, and that would be because my base is bigger than 1, right? My base is 3. So what are my 3 key points for y equals 3 to the x? Feel free to use your notes if you don't remember. We input -1, we input 0, and 1. What would our outputs be originally before we incorporate the transformation? Yep, it would be 1 over my base, so 1 over 3. It would be 1, and it would be my base itself. So 1 over base, 1, and my base. Okay. That's the original situation. But now we have a transformation, and we studied those in an earlier module you might need to go back to, perhaps. What did it mean to subtract a number at the very end of a function? It meant to go left to right, up or down? Down, good job. It meant go down that many units, which affects the y value, right? So if I rewrite my y value, my final 3 key points would be -1, comma something, 0, comma something, and 1, comma something. I'm going down 2, so my y values are reducing by 2, or going down by 2. 1/3 minus 2 is really 1/3 minus 4 over 2, right? Or 1/3 minus 4 over 2 would be what? Well, I actually said that wrong, I'm sorry. I meant to get a common denominator of 3, and I got a common denominator of 2. My bad. 1/3 minus 2 would really be what? 6 over 3? Yeah. So what's 1/3 minus 6/3? -5/3. That's what I meant to say. Apologize, but maybe you would have done the same thing. Okay. What about 0? Well, if you take 0, it was originally at an output of 1. Subtract 2 from 1, what do you get? 1 minus 2. That's right, -1. 1 was originally giving you an output of 3, but if you subtract 2, you're at an output of 1. So let's see what that means on our graph. We're going to sketch our graph with these final 3 key points after our transformation has taken place. So the graph of y equals 3 to the x minus 2. It should still be growing, but the graph has just been shifted down 2 units. So that would be at -1 and -1 2/3. So -1 to the left and down 1 2/3 around here. 0, -1 would be here, and 1, 1 would be here. Now, where is my asymptote supposed to be? Can we remember where it was originally? Yeah, originally the horizontal asymptote is always y equals 0. We got to memorize that for an exponential growth or decay graph, y equals b to the x. So if I've moved the whole graph down 2 units, that has affected my asymptote, hasn't it? So my new asymptote is 2 units lower. Y equals what? Negative 2 is my horizontal asymptote. So I'm going to draw that as like a dotted line to tell myself that's what I should be approaching as I go toward the left forever here. So let's draw our picture now. Get closer and closer to that line, 0. And as you go toward the right, you're shooting up rapidly. That's what exponential growth is doing. Domain, all real numbers, negative infinity to infinity. Range, how low can you go? It used to be 0, right? But now it's moved down to. So anything above negative 2. In other words, parentheses, negative 2 toward infinity. So those would be what I'd be looking for on a test question if I ask you to draw a sketch of an exponential function after transformations. Try the next one on your own. Y equals 3 times 1/2 to the x power. What does this mean? Well, go ahead and try and see how you did. Originally, I would notice that I have exponential decay. And the reason it's decay is because my base b is 1/2, which is between 0 and 1. So this is a graph which is getting cut in half each time. If I was starting with those 3 key points, they were negative 1 for an input, 0 for an input, 1 for an input, with a horizontal asymptote at y equals 0 originally. But the 1 over base here would be the reciprocal of 1/2. We did this earlier. The reciprocal of 1 over 2 is 2 over 1. It would be 1 at 0, and it would be my base, which is 1/2 at 1. So that would be the original situation for y equals 1/2 to the x. It should be exponentially decaying. But what did the transformation this time do to us? Putting that 3 in front was a vertical stretch, if you remember from a previous material we've learned, which meant a vertical stretch is when you multiply the entire output or the entire y value by that number, and that number happens to be bigger than 1, so it's stretching out the function's graph. If it was less than 1, it would be a vertical shrink or compression. So let's make our y values 3 times as big. So triple those y values. Your final 3 points then, if you triple your y values this time, would be, for your final 3 points, when you have an input of negative 1, negative 1 would give you 2 times 3, or 6. Positive 0, or just 0, would give you 1 times 3, or 3. And positive 1 would give you 1/2 times 3, which is really 3 over 2. You might need to work with your fractions a little bit there. 3 over 2 is 1.5. So let's graph our 3 key points for this exponential decay model. At negative 1, 6, this function, f of x equals 3 times 1/2 to the x, would look like left 1 up 6. Oops. I think that's right there, actually. So let me erase that by accident. Our next point should be at 0, 3, 1, 2, 3. And then at 1, I should be at an output of 3/2, or 1.5, so around here. And our asymptote, has it changed? It was y equals 0, and then we multiplied our y values by 3. Does 0 times 3 change? No, it's still at good old 0. So your asymptote is still 0. It will only change if you moved up or down. Here we just multiplied our y values to stretch them out. So our graph should just be a little more stretched out than the original. And if you went to desmos.com and looked at the original 3 to the x versus, 1/2 to the x versus 3 times 1/2 to the x, you're going to see the slight stretch that has happened in our function. For domain and range, still all real numbers apply. Any input is legal for our x value, left and right forever. But the range is 0 to infinity this time. Any output above 0. I think there's one more for you to try. This one really you should try on your own if you haven't already to get some confidence. It says, can you sketch this function, f of x equals negative 4 to the x plus 1 power? Try it on your own. So if this were me, I would notice this is exponential growth because my base b is 4, which is bigger than 1. So I'm expecting the picture to be growing. The original key points for exponential growth or decay are negative 1, 1 over my base, 0, 1, and 1 my base. So negative 1, 1/4, 0, 1, and 1, 4. Horizontal asymptote originally at y equals 0. So if you think, wow, she's going fast, feel free to slow me down, but remember you can become fast too with much practice. Okay. What else do I need to notice? I need to notice that there are 2 transformations going on. If you forgot the order in which you apply them, you always start inside the function and work your way out. Now, you might not think there's anything inside, but when we say exponent or square root or absolute value, anything like this, that is implied to be inside the function. So the exponent is like being in parentheses. So that's where we begin. That's our first transformation, which is really moving to the left. Good job. It's counterintuitive, wasn't it? So you might need to go back to your old videos and look at transformations of basic functions. If I'm moving left one, that affects my x values, doesn't it? So change those x values. Instead of -1, I'm at -2. Instead of 0, I'm at -1. Instead of 1, I'm at 1 minus 1. That's 0. Now, you could separate these out and say that is at the output 1/4, 1 and 4, and then go to your second step. Actually, I would recommend that. So let me just do that real fast. So -2 changed, -1 changed, 0 changed, but these stay the same. 1/4, 1, and 4. But now we have one more transformation to take care of, don't we? What does that negative in front of the entire function do? That's right, our second thing is to flip it or reflect it. But how? How do I reflect it? Do I reflect it across the y, or do I reflect it across the x? Well, you're changing the sign of the entire function, right? You're not just changing the sign of x like you would if it was right next to the x here. So instead, if you're changing the sign of your y values, that means if you're changing the signs of your y values, if it was positive, it becomes negative. And if it was negative, it becomes positive. So you're really folding over the x-axis. You're reflecting over the x-axis by changing the signs of your y values. So your final 3 points, if you wanted to write these out, would be, let me grab my color, there it is, -2, comma, -1/4, if I change the sign of y, -1, comma, -1, and 0, comma, -4. So let's see where that would be on our graph. Let's grab a color. So this graph, f of x equals -4 to the x plus 1 would be -2, 2 to the left, and down 1/4, so right around there. -1, -1 would be left 1 and down 1, right around there. 0, -4 would say go down 4 directly from the origin. 1, 2, 3, 4, right there. So our graph is looking interesting. It was originally growing, right? So it was originally something like this. Then it got shifted to the left 1 unit, so it's still something like this. But now it's folded over. So it should be looking something, if I can graph it not too ugly. Sorry, it was a little rough. Something like this is happening. It's been flipped over, and it's still approaching its same asymptote, y equals 0. Why is that? Well, the graph never moved up or down. The only time the horizontal asymptote y equals 0 will change is if we move the graph up or down. So the asymptote is still right there. We're still getting closer and closer to 0. Your graph should be a lot curvier, so check out the Desmos graph below. Click on that link, or type it in yourself into a graphing utility, and you can see the actual curvature that it should look like. I'm just doing a very quick sketch for you. Now, for a domain, all real numbers are still allowed. Any input is allowed for a domain of an exponential graph. But the range just changed. What outputs are generated potentially? Are they ever positive? Are they ever negative? Are they one or the other, a mix? They're always negative, aren't they? Because the graph flipped over, now it's always below the x-axis. In other words, all of your y values have to be below what number? That's right, they have to be below your horizontal asymptote. In other words, they're below 0. So 0 is your highest, your lowest would be -infinity. Some people ask me at this point, does it matter if I put the 0 first or the -infinity? Absolutely. You always want to put the lowest on the left and the highest on the right when you're talking about y values for range. If you're talking about x values, you want to put left, the furthest left, and the furthest right. So order is important in math. I hope we make that clear by this class. All right, so at this point, we've now introduced what does it mean to be an exponential function? What is exponential growth versus linear growth or decay? We've also talked about what key points you need to memorize and what the basic shape should look like for an exponential growth or decay model. So now it's up to you to memorize and to practice, because math is not a spectator sport. And I'll see you next time.